All right. Good afternoon. We should get started. So it's my great pleasure to introduce today's distinguished speaker, Garnet from Caltech. So Garnet is a Grand Professor of Chemistry and the Director of Global Market Center for Theoretical Chemistry at Caltech. And then, as many of you probably are aware, so Garnet is a leading theorist with expertise in a wide range of interdisciplinary areas, including theoretical chemistry, condensed metaphysics, and quantum influence science. And in particular, this group has been consistently developing state-of-the-art numeric algorithms to study many other phenomena and tackle challenges associated with quantum advantages. And today, we will be talking about basically classical simulation of quantum membrane systems. So please join me in welcoming John.
Okay, great. So I'm speaking without microphone. Hope you can hear me. It used to be when you went and gave a colloquium, if you gave it in chemistry department, know your audience, physics department, know your audience. But now you use quantum colloquium, and you don't really know quite who you're talking to. So I was going to just quickly poll, how many who's from which area. So if you're from AMO, can you just raise your hand? Okay. Okay, that's most of you. Okay, condensed matter. Okay, that's the other half, basically. I think quantum complexity people. Okay, one theory. Okay, I have that one slide for you. Chemistry. More than I thought. Okay, that's right. That's not right. I can't see if I'm wearing the wrong glasses. Okay, but maybe on. Okay. Yeah. Okay. So of course I'm a chemist by training, but I noticed on my schedule that basically no chemist except for Grant. So I'm not actually going to talk about any chemistry today. But if you're interested in that area outside of my work, I'm happy to tell you about it in my video. Okay. So basically I'm going to talk about how we simulate the quantum phenomena that we study in science using classical computers. And this is the kind of stuff I'm going to talk about. So we'll first start with a slightly philosophical question, like why is it that we're able to simulate quantum systems, which obey the laws of quantum mechanics, the classical computers, which seem to not naturally follow the laws of quantum mechanics. And then I'll spend some time on a specific example of a quantum many-body system where we've done many classical simulations. So for the sake of limiting the scope, this will be focused on the problem of high-temperature superconductivity, both in models like the Hubbard model, which AMO, of course, are interested in, as well as in datable representations of the real material as well. And then finally, we'll get through this if we have enough time. I'll briefly talk about work in non-equilibrium mass and the prospect of classical simulations of models. Okay, so just to start with, when I'm saying I'm simulating a quantum world, my personal interest is really what I call ordinary matter, right? So this is just matter that you can make and hold in your hand. It's relatively stable, and you can study it in a laboratory rather than extremely exotic and synthetic matter. And ordinary matter is made of, so let's say the molecule or material, it's made of atoms made of electrons, nuclei, And especially the electrons at ordinary temperature pressures are very quantum mechanical, and so you have to use quantum mechanical equations. So essentially, my main area of research is about using computers to simulate ordinary matter using the laws of quantum mechanics. And when you start out in this endeavor, you very quickly run into what seem to be some large challenges, at least conceptual challenges. And, if you go all the way back to the founding fathers of quantum mechanics, you'll find some statement already early on that although they knew the quantum mechanical equations, the Schrödinger equation, the Dirac equation, which in some sense fundamental equations of the universe. Solving these equations is very hard. And although Dirac didn't sort of state this in complexity terms, I mean, what he really was indicating, what we say today, is that some worst case cost of doing a quantum simulation of a large system is really just exponential in the system side, which you can rationalize because the Hilbert space in which the state is just exponential in the system side. So if you hear that for the first time and you take this as a starting point, that leads you to be very pessimistic about any prospect of learning anything at all about the world using quantum mechanics. Everything is just exponentially hard. But what has actually happened in reality in science in the last 100 years since Dirac's statement is this challenge of solving these equations has actually been met in many cases, and really simulating molecules and materials with some degree of precision is a routine task that's carried out by people every day. And this has been both because we now have a lot of physical insight into the types of quantum states you see in nature. So we, in some sense, have learned from the natural world. And we have also developed algorithms that use these insights so that we're able to make precise calculations. So if you look at, what is it that makes quantum simulation with classical computing possible? There are really three primary ingredients to make it possible. The first, as I say, is we actually have looked a lot and studied a lot quantum systems, for example, in the lab, experimentally, and we know a lot about what the quantum states, how the quantum states actually behave. In its most abstract form, this is perhaps the theoretical exercise of classifying quantum phases, and we know a lot about the types of quantum phases that natural Hamiltonians support. Then secondly, and this is kind of more in my domain, based on this qualitative understanding, we can devise algorithms that use this information to do quantitative simulations. And these algorithms, I usually call them heuristics because they make assumptions. I mean, they're assumptions that come from your knowledge of the natural world. But with these assumptions, then the problem is not so hard. And that's building these algorithms is an activity that is spread across many areas. So, for example, I am trained as a quantum chemist. That's how I entered this field. But of course, people for this theory work, this people in quantum information theory work. That's why when you work on algorithms, it's kind of a nice way to talk to many different people because we're all just solving the quantum many. And finally, the last thing, of course, is what we have, something that we have that Dirac did not have. Right? Was that we have everything. But I'd like to emphasize that, although computing power has increased a lot in the last 100 years, when we say Moore's law means there's this exponential growth of computing power, this is not the primary reason why we're able to make progress, because in principle, the worst case complexity of quantum simulation is also exponentially growing with system size. And so if you were to just follow Moore's law and say every 2 years, I double my computing power, that really just means I can simulate one additional qubit every 2 years. And so you have to wait a long time to simulate material. So this is a piece of the puzzle, but really the most important thing is these first two, the intellectual core of this. And so just to spend a little bit more time on these two ideas, when I say we have a lot of insight into what natural graph states look like, what I mean is when you look at materials in the low energy sector, the graph states, the low energy excited states, you'll find very quickly that they only have a few types of qualitative behaviors. These are all the materials we know. This is what we call, of course, phase, quantum phase. For example, insulators, metals, superconductors, these are very, I guess, traditional phases. We knew about these ordered phases, there's electronic crystal. And also perhaps more exotic things, where the order is harder to detect, like topologically ordered phases, so forth. I mean, there's a long list that one can write down, but in the end, it's still just a long but not it's this exponentially big list that you really have to consider. And then what is also remarkable and perhaps slightly mysterious is that in each of these cases, you can actually write down very simple mathematical theories to describe each of these phases. For example, for metals and for liquids, for superconductors, broken symmetry orders, and that helps with symmetry breaking. For any topological complex fraction form ordered Lofton wave function. What these theories are is they're just concise classical descriptions of the quantum state. That's what the traditional theory is. And so consequently, because we have these very simple starting points that are amenable to classical, that really is a classical description, and because the number of these starting points is not very large, we basically can take as an assumption that the lower degree quantum states in nature are really just understandable and they're not really exponentially complicated. At least that's what the natural world suggests. And consequently, we can devise computational algorithms that don't encounter this exponential complexity because there just isn't an exponential set of possibilities to explore. So I was on sabbatical last year, and in sabbatical I had some time to do some more writing. And so one of the things that I did was I wrote some very long educational essay about quantum chemistry that is intended for people in quantum information to read, so we could try to couch some things in terms that you might relate to if you work in quantum information, and it's also meant for quantum chemists so that they can understand, use some words from quantum information theory. It's published in this journal that I know everyone reads all the time. It's basically also memorial lectures. It's published somewhere, but you can find it on the archive. But also in this essay, I tried to make the philosophical statements I said previously a little bit more precise so that they can be analyzed from a more theoretical standpoint. And so I think in essence, what I'm trying to say, and what is a working hypothesis of someone who does numerical simulation, is that the classical cost to simulate ground state in this sort of ordinary matter takes the following form. The cost has some prefactor, which is associated with doing some search over the type of order you think might be in. So some search of these classical descriptions. So you expect it to be some kind of NP-like complexity. And then starting from that starting point, you then apply some heuristic to get a qualitative answer. So you refine the result. And one can find numerical evidence, and I give numerical evidence here, for example, that the form of this refinement cost is polynomial system size and polynomial percent. So I call this, a conjecture about the classical cost of simulating ordinary matter, and the difficulty in analyzing the statements a little bit, really how to define ordinary matter. Right? That's a little bit different. We'll see as perspective, but I think it's something that I want to begin to analyze. The interesting thing about this form is that if you take quantum algorithms with provable complexity for ground state energy estimation, like phase estimation or quantum linear algebra, then it has the same form. Right? There's a prefactor associated with preparing an initial guess, which, because your initial guess has to have some resemblance to your final result, should be in the same phase as the final result. Should have the circle of the phase is. And then there's a refinement cost, and the refinement cost in the quantum case is provably performed polygon of the epsilon. So comparing the two, of course, raises many interesting questions. I mean, first, can I prove the statement under some suitable conditions? If you are complexing theorists with interest in this problem, I'm very interested in talking to you. And of course, it raises questions about the implications for quantum advantage, which is what the rate of cost. But that's not really what I'm going to focus on today. Today we'll focus on practical The practical implication of everything I was saying is simply that in practice we can simulate a wide variety of interesting problems without really getting an exponential law. And so, in my group, we work on molecular problems and sort of biochemical problems. Not really the interest of this audience. What I'm going to focus on today is some of the work that's more in the dense matter field. That's what I'll spend most of the time talking about. And then at the end, I'll talk about some quantum mechanical dynamics, including circuit. Okay. Right. So quantum anybody problem. So we have to pick one, and perhaps the most famous one in condensed matter is still the problem of high temperature superconductivity. It's an old one, but it's a good one, right? And it's been around. The cuprates are most famous example of these materials, still with the highest TCs and ambient pressure. They've been around now for 40 years, really long time. And there have been a lot of papers in this field. I don't have a current count. The number is going to be rapidly overtaken by the number of papers in quantum information. That's really good. There's been some doubly exponential growth. But in any case, there was a lot of papers written in this field. And I think it's fair to say, though we do know a lot about cuprates and high temperature superconductivity, I think it's still fair to say that we cannot predict, people cannot predict what new materials might be superconductors, or even if you took an existing cuprate, what do you do to it to make it better? So those are critical questions that I'm quite interested in. So the reason why we can't answer this question of how to find or make a better high TC material is not because we don't understand superconductivity itself. Superconductivity is actually a very simple phase of matter. If we were to just take three particles and add an attraction to them, add an attractive interaction, then the natural ground state really is a superconductor. Very natural. So the only real question is what generates the attraction between the particles. And if your charge carriers are electrons, say, then they will repel. So the way to generate an attraction is that it has to be generated in an effective way, via other constituents of the system. And in the traditional mechanism, then naturally you think of the electrons as interacting with the ions or the vibrations, and via this interaction with the vibrations, it can sort of engineer a weak attractive interaction. The only issue, as I say, is it's weak, and so the small amount of thermal fluctuation is sufficient to destroy this pairing interaction, and you can't support, this critical temperature of the cuprate materials. So there has to be some other way in which the electrons are effectively attracted. So what might be happening? Well, one can get some perhaps cartoon of what might be happening and some hint of what might be happening by looking at the phase diagram of these materials. So here I show the phase diagram of the cuprates. So the phase diagram looks very similar across all the different cuprates, and even if you take these iron-based superconductors, which are also kind of high TC and not super high TC, they have a similar phase diagram to this picture, not quite identical. And the phase diagram basically just says, as a function of some parameters, what phase of matter are you in? So the function of temperature on the y-axis, and the function of doping, you put some additional charges in the system on the x-axis, then your cuprate material will be in different phases. Now, if you focus just at very low temperature, let's say 0 temperature, then you see that if you put no extra charges in, your material is actually a magnetic material, an anti-ferromagnetic neodymium insulator. And then only when you dope it, a bit, does it become in the superconducting phase. And this is common, like I say, to all the cuprates, and this is also how iron-based phase diagram basically looks. You have some magnetic order to start with. And so one might think the magnetism has something to do with it. And one can make some sort of cartoon of how magnetism might lead to the attractive interaction. So if you draw the initial anti-ferromagnetic state, you have a nice checkerboard pattern of the magnetic moment, for example, at the low energy configuration. And you can think, well, what happens when I stick charges in? So when you stick charges in, you break up this nice pattern. and you break some of these nice antiferromagnetic interactions. So there's sometimes some energy penalty that has occurred because you've broken a lot of these antiferromagnetic interactions. And then just in the same way that when you stick oil into water, the oil will like to stick together to minimize the surface area so it doesn't break so many of the water-water interaction, then it seems natural that if the charges come together, they minimize the antiferromagnetic disruption of the antiferromagnetic background. So sounds plausible, right? But perhaps this is what's going on. But this is just really a cartoon, right? This is not a theory. And the truth is, of course, if you just think at this level, you can think of many proposed mechanisms for how to generate the attraction between the electrons, which is why this has always been a contentious field. So to make any real progress, one has to move beyond this type of model building problem. You have to simulate some concrete problem. So this is where numerical simulations are important, because you can just say what is actually happening in some specific solution of a problem. Okay, so our approach to understanding things will not be by this model building, but by solving concrete problems. And so we have to choose some level of description of the throughput material. And so of course the material is a very complicated thing. It has lots and lots of atoms, and the real material has lots of electrons, it has lots of orbitals and lots of bands. Usually in condensed matter theory, however, one doesn't start from this end. But instead, one tries to solve a simpler problem. And historically, about the simplest problem that you can make out of the throughput material is this problem on this left-hand side, known as the Hubbard model. Many of you will know what it is, of course, everyone here. So the Hubbard model basically takes an entire unit cell of material and simplifies it down to a single site. And then the single site can just contain 0, 1, or 2 particles, and these particles are fermions. And when 2 particles on the same site, they experience repulsion U. Otherwise, they just hop around with the kinetic energy that does not have any scale. So what I'm going to start with this talk is about understanding the Hubbard model and just address the question, how well can we just solve this Hubbard model, and perhaps that will reveal something about what's going on with the height of the superset. Okay, so the Hubbard model is an extremely simple model. It's only got 2 parameters, but historically it's been real graveyard for numerics. I started working on this particular aspect of things about 2010. And if you looked in around 2010 and asked, what do different computational people you normally respect, you think that they're honest people and not try to trick you, what do they say about the ground state of the Hubbard model? And you'd find many different kind of predictions. Okay, so all these acronyms are not too important, they're different numerical methods, but the different colors here are different type of orders that people are saying exist in the same region of the ground state, and you see the colors they don't match up. And so you can ask, why is this, like I said, these are all honest people, why is this state of affairs, happening? And what's really the case is just that the Hubbard model as a model has a kind of degeneracy in the orders that it supports. And so when you're doing numerical calculations, if there's any bias in your calculation, you'll just go towards one type, predict one thing rather than the other. And so there are these small energy scales that you need to resolve. And if you want to make concrete statements, you really have to grind down on the accuracy. Fortunately, in the last decade, or the time since, a lot of progress has been made in improving the some of this has come by new algorithms based on new ways of thinking about the concept, and some from implementation, and some, of course, just from the increase in computing power. But to give an example, around 2014, 2015, I was one of the people who helped to initiate the first Simons collaboration, and this was a collaboration in the area of quantum many-body physics, which brought together different numerical theorists to try and make some concrete predictions, largely about the Hubbard model. And in the very first test we did, we picked some points in the phase diagram. It's a relatively simple point, but nonetheless, it's something like a phase diagram. And we tried out all these different techniques, which had honed to the best that we could. and try to predict the ground state energy, this is the first slide, to the highest accuracy we could. And we found that, in fact, it was possible, after all these advances that have been made, to obtain many decimal places, basically 4 significant figures. And like I say, some of this comes because of new ideas. So the last few entries in the table did not exist in 2010. It was a different way to think about doing quantum simulation. And others like AF, like QMC and DMRT, these have been around for a long time. But there are some improved implementations that allow them to achieve higher accuracy. And to see the improvement relative to when things were in 2010, here is some number from technique, okay? And you can see that in 2007, you compare this energy to this, there's only one significant figure. So there was a really large advance in the 10 years of these two results. And then based on this new capability, it then became possible to really think about just solving for what we ground state in the Hubbard model, once and for with like definitive accuracy. And the first place where we did this was in some work which I led together with some other collaborators, where we looked at tried to identify the order in the Hubbard model ground state at 1H doping, which was always a very contentious point. 1H doping is a point in between the magnetic phase and where you might expect a superconducting phase, roughly speaking. So just somewhere in between, and then when it's in between two things, people will say many things, different things can happen. So this is actually very complicated for the phase diagram. We cannot get quite the same accuracy as here. We don't get 4 significant figures, but maybe 2 in a bit. But what we could, with that level of resolution, identify that a specific type of order where the charges that are doping into the system with this amount distribute. You could identify the charges and the magnetic modes distribute themselves in this inhomogeneous pattern that is known as a stripe. So essentially, what we could definitively say is that the stripe order is more stable than any other order that we would have proposed. Okay, so moving rapidly forward to the current day, I can sort of just tell you what the state of the art is today. I mean, today I don't focus so much on the Hubbard model. I tell you more about what they work mainly later. But we think about what is the best you can do for the Hubbard model today. Here are some recent numbers from my own group, which are the most accurate numbers in the system. So today we can basically simulate a ground state on arbitrary large lattices at any point in the phase diagram to about 0.5% in accuracy so that's about 2.5 figures. So basically any roughly 2.5 decimal places basically everywhere. Now, when I say we can simulate arbitrary large lattices, that what I really mean by that, what I mean is you can use simulation methods whose cost scales linearly with the number of sites. So, here I show a simulation on 256 sites at 1H doping. This is showing how the stripe looks like when you have a two-dimensional version of the problem. And the cost is just linear in the number of sites. This took a couple of days. So we want to simulate 1,000 sites. This is definitely possible. And to illustrate the accuracy that we can get, this gives you kind of a sense of where we are. So these simulations were done if you're an aficionado by some type of variational ansatz as a fermionic network, using stochastic evaluation, using Monte Carlo to make the scaling low, because that's technically what was done. And here I show the accuracy that we're getting, relative accuracy, the 0.1 is 10%, versus the variational freedom in the ansatz, which is measured by this parameter that is on dimension, but it's basically related to variational degrees of freedom. And on some physical scale, 10% accuracy in the Hubbard model energy, if you take the units of the Hubbard model and try and convert it into material units, like the cuprate units, 10% corresponds to a basic error on the scale of about 300 Kelvin. So if you simulate to 10%, it's not very good if you want to study things about superconductivity, which are currently at about 100 Kelvin or lower. But I think we'd all agree if you can simulate with an accuracy that's on the order of a few Kelvin, let's say 3 Kelvin, you can probably resolve all the physics of the ground state to at least superconductive type fluctuations. So where we are, if we take the sort of largest type of variation waveform we can simulate today, with modest resources, is we're about a bit better than 0.5%. And you can extrapolate to understand what kind of simulation size you need to do to get to this 3 Kelvin accuracy. And you can conclude that roughly speaking, if you put in about a 50 to 100-fold increase in effort, then you should be able to get to this accuracy. So it's something that, yes, go.
I was wondering, I mean, there's like a bit of a turnover in some of those plots.
Oh, yes.
Higher bond dimensions. It's clear that these are actually sort of scaling.
Yeah, so, this is very likely because when you go to these larger bond dimensions, the calculations take longer and you're doing these optimization and you get less patient with running as many optimization steps, that thing. So that's basically the origin of these type of things. They're not at all. But
sorry, would you mind saying what energy accuracy?
Yeah, so you're just computing. Oh, you mean are you saying how do I estimate the energy accuracy, or what does
what's on the y-axis?
The y-axis means I take the energy versus what I estimate to be the exact ground state energy and divide it by the exact ground state energy. So it's a relative accuracy.
And how does one estimate the actual versus?
Yeah. So for example, if you have one of the narrower systems, then you can estimate it from other methods that work on narrow systems. So for example, you can do DMRT on a 4-site or even a 6-site ladder, and obtain almost exact estimate. That's how it's done for 4 and 6. And then for 8, we use some extrapolation. Yeah, exact ground state. That's why this is not done on the 16 by 16, because on 16 by 16, we don't have an exact estimate. But everything we understand about the ground state and the ansatz that you use, ground state is basically some area law ground state. We don't expect the accuracy to be extremely different if we increase the size of the system, so long as the answer from that point. Okay. Okay. So this just gives you some way to understand, where we stand. Like if civilization depended on it, okay, we could probably engineer our code and use enough computing power today to simulate 2.1% accuracy. But if you want it to be a routine simulation, run on modest resources over just a few days, this may take something in the next 5 to 10 years. I think where this accuracy. Okay, but I talked a lot about solving the Hubbard model very accurately, but we can ask, is that really worth it? And is this worth it in the context of the question that I'm personally interested in, which is like, how do I make materials which can have a high TC? And the answer is, it sort of depends, because there are people who are extremely wedded to this model, and they would say it's a fundamental model, we need to know the answer. But if you start, now that we're able to obtain accurate data in the groundscape, we can actually begin to see ways in which the model fundamentally differs from the material that it was originally meant to represent. So some original examples of this was if you looked in the underdome region where we found this celebrated stripe, indeed, it's nice to see that the model supports this very inhomogeneous pattern of charges and moments. But actually, the wavelength that you find is this very long wavelength stripe. And in real materials, the stripe wavelength is much shorter. But in the pure Hubbard model, at least, the short wavelength stripes are much higher energy. And if you look at superconductivity, its inductive order, which is what the Hubbard model was there to first describe, it's not really clear that the Hubbard model really supports superconductivity if you don't fine-tune some things, if you don't tune some of the parameters, or at least the superconductivity is very weak. And so this comes from lots of different kinds of work that suggest that superconductivity is either very weak or in the wrong place. But taken in totality, my personal perspective is that if you're interested in this materials question, how do I make the best material? How do I engineer group rates to have higher TC? The Hubbard model is really just a suggestive model, and it has its limitations. And so, for that reason, a lot of my work in this program of research for the last 7 to 8 years has really been trying to move beyond this model description of material and really to an actual atomistic description where all the atoms, all the electrons are actually in the Hamiltonian star. Okay, so can we really just study high TC in this faithful simulation of materials? Okay, well, So to do this, one first has to define some type of computational framework which is flexible enough that you can actually deal with this very complicated Hamiltonian. Many of the techniques I described earlier that are used in the Hubbard model really can only be used on the Hubbard model or very similar models. And you start to put in, 1,000 bands or so and so forth, it's impossible to have those techniques. And so you first have to define a tool that, it's always sufficient in accuracy that you don't lose all the physics, but which is flexible enough to treat a very realistic Hamiltonian. And so we can ask, well, what sort of framework might that be? And so if we go back to the very general terms, we ask, what is superconductivity? Well, it's just some broken symmetry phase. And so going back to just how we think about these broken symmetry phases emerging in matter, they emerge in some approximate energy or approximate free energy functional as some minimum of that energy, some minimum in this nonlinear energy function. And the simplest example of some type of nonlinear energy functional or some kind of self-consistent energy determination is just mean field theory for single electrons, what we might call Hartree-Fock theory, where you determine the wave functions of individual electrons, but the whole thing is nonlinear because the Hamiltonian for these electrons depends on the other electrons that you have to determine this in an iterative way. So this type of nonlinear theory, this Hartree-Fock theory, if you apply it to materials, you will find that in certain parts of the phase diagram, in certain materials, you get new phases. For example, you get magnetic phases and non-magnetic phases. But we know, so from a rigorous result from Elliott Lee, all the way back in the 70s, that if you just have repulsive interactions, which is what we have with electrons, the native repulsive interaction, you cannot have a superconducting solution of this. So all the minima are either magnetic or non-magnetic, but they're no super. So one might think, okay, let's just design a more sophisticated version of this process. And rather than having a single electron as the self-consistent object, a single electronic orbital, maybe let's make some many-body object, maybe something with many electrons. And one way to construct such a procedure would be to say, okay, let's think of the crystal as made of lots of unit cells. It's a crystal. And I can think of solving this bulk problem really as just solving perhaps a cell of the problem or some subset of the cells in some approximate description of the environment, which I'll call a bar. And this is a self-consistent process because this approximate environment is actually just made of all the unit cells. So although it has to be an approximation, otherwise I have to solve the full bulk problem, every time I improve my description of this unit cell, I have to improve the description of the environment. So you have to have a nonlinear energy function like this. Okay, so this is general class of computational techniques, or what I refer to as quantum embedding techniques. And they have some nice features. Although they are a type of mean field, they are, when you say mean field, it sounds like the answer is like always wrong, mean field, okay. But this is a type of mean field that can be made exact because it's clear if you just take larger and larger chunks of matter, then eventually you assimilate the whole thing, right? So there's a way to consider a sequence of these mean fields and infer what the correct answer is. And then more importantly, for this specific application, in simple models like the Hubbard model of group rates, it's been known for a long time that this type of nonlinear energy functional does support a superconducting ground state for purely repulsive interactions. The evidence really comes from a type of quantum embedding known as dynamical mean field theory. The details are not too important, but essentially in work on the Hubbard model back 25 years ago, what these people did, such Lichtenstein and Snelson, they cut out a small 2x2 cell, right? Solved for it in the presence of some approximate description of the environment and iterated this procedure. And the results they got out look like this. Okay, so the top part is the experimental phase diagram two phase that I indicated earlier. Just pictorially, there's an anti-ferromagnetic phase, superconducting phase with functional doping. The bottom is what they compute. As a function of doping, they see, now they're not computing a critical temperature, but they find a solution which is a magnetic solution, and it has some order parameter which decreases as a function of doping, a little bit like this temperature line here. And they find a superconducting solution which, through the order parameter, has a peak at intermediate doping. It's not exactly the same quantity, but if you assume that large order parameter correlates with high critical temperature, then there's a great resemblance between the two. Okay, so it's very, very suggestive. Now these are old results, of course, but they suggest that even this like simple computational framework, even though it's approximate, perhaps it contains correct physics, but these kind of results have always been a little bit, controversial or not fully accepted, I would say, in sort of public model community, for the reason that this is a small cluster, and so it is really just some kind of neat field, and you have to really want to go to a large cluster to remove the neat field data of it. And then furthermore, for the purpose of what we want to do, this kind of technique, work is very easy to implement in a Harvard model, but it's actually, the Harvard model is not really material. And when we start looking into dynamical mean field theory and work in this area around 2012 or so, we realized that both these limitations are very challenging to remove within the mathematical structure of dynamical mean field theory. So the first thing that we did, therefore, was to try to create a computational framework which has the spirit of this quantum embedding, but which is easier to extend to large clusters and easy to extend to large Hamiltonians. So for that, we need to understand why dynamical mean field theory is computationally, tricky. And essentially, what you do in dynamical mean field theory is you compute the Green's everything with all the Green's functions of the problem, and so the Green's functions contain all the spectral information, so it's great, we can do the Green's functions. But it comes at a cost because it's a dynamical quantity, and computing dynamical quantities, you need to put a lot of computational effort into that. But superconductivity is an equilibrium property, and so if you just want to study, the order and determine if something is in a superconducting ground state, you don't really need all that information. And so one can formulate a quantum embedding theory where rather than solving all this dynamical information, in fact, you just solve a time-independent function and just compute the static information. And this is something that we call density matrix embedding theory. Essentially, it's formulated in terms of the density matrix, or the mixed quantum state of the thing that you're cutting out. And this is something, because of this much simpler formulation, was in practice much easier to extend to large clusters. So you can remove the mean field nature of the approximation, and you could use it with very complicated like animation. So I won't go through the entire story of where that started, just to go make things very quickly. We spent a number of years benchmarking it in the Hubbard model just to show it's a sensible thing to do and can really get state-of-the-art results. That's some things I covered earlier. But in 2016, I moved to Caltech, and one of the projects I decided I would start there was to use this framework that we had been developing for this purpose of simulating the true material. So if you move from the Hubbard model to the real material, you move from a picture right like that to this, okay? And it's moving from essentially like one band physics to say a few hundred or a few thousand bands. From a very theoretical perspective, there is no difference between the two, because we would say 1,000 bands is all high energy stuff. The low energy effective model is all gone, okay, and that's all true for the universe. You take a very universal picture, but of course, the quantitative details matter. But it is true that all the stuff you're adding in is essentially perturbative in nature. It's the high energy stuff that you've integrated out. Okay, so there's some simplifications in treatment, and that's why it can be done. So this is what quantum chemists do every day, right? When you study a molecule, you don't study the low energy. Of course, usually you're not treating the high energy modes of the nuclei, but in some sense, you're not treating a low energy model. You're doing the real Hamiltonian because wanting a very precise answer. And it's got many degrees of freedom, many orbitals, but we're able to do it because they're largely perturbative effects and not non-perturbative effects. So going from here to here is basically building in all that quantum chemistry technology into the problem. And that's just technology building. Many of you build instruments. It's really the same thing. You spent a long time building technology. And one of the first things that we built was this package to simulate basic quantum chemistry in materials. This has developed a life of its own. This is how it all started, but it's used all over the world. So in many industries, I got a statistic. We had a developers meeting like a few weeks ago, I had a statistic. Last year, it was downloaded 1.2 million times. And I do not know what people are doing with all those downloads. It blows my mind, actually. But it all comes to a lot like machine learning and so but anyway, this is how it started. And then we had to put this technology of prompt learning into this. That took another few years. And just in case anyone is under any illusion, sometimes they get this talk. I'll show you all this effort to build a spatial simulation, and at the end, people ask, so what was the parameter of the Hubbard model you used in your simulation? The key point, we're not solving the Hubbard model. Okay, so we're really solving the 1,000 band. Okay, this is really what we do. All right. So this took a number of years, and it kind of took us into the early days of the pandemic. And then sometime, around that time, I remember my student Jihao telling me, okay, it's finally good, we're finally working, got the last bugs out. We really do a calculation. And so we had to decide what's the first thing we're going to simulate with this gigantic machine. And my suggestion was that if you look at two-phase materials, they have some very well-known trends. Okay? People might not know why they have these trends, but they actually have this trend. And if you look at, say, just the parent state of the material, which is the simpler case, it's not superconducting, it's this antiferromagnetic state, there's a trend in the magnetism in the sense that if you take materials with more layers in the unit cell, then in a certain sense, the magnetic order is stronger. You can define what I mean by this, but in some sense, the magnet is stronger. So this is something that I've never really seen an explanation for, certainly no one ever simulated it. And so the first thing was just to see if we can reproduce this trend and then say where it comes from. And to make the long story very short, the answer is indeed would be just put these crystal structures in, compute everything, get the magnetic moments out, extract the effect of exchange couplings, for example. You see that as you increase the number of layers, then indeed the exchange couplings all get stronger. So you have this trend. And if I were to predict the Magnon spectra, that's a spin wave spectra from these materials, we can actually compare to them term. So these are measured by Rix or across these series of materials. You see there's an energy scale that's increasing. And the computed ones are these blue lines, right? It's not completely quantitative, but you see the same trend.
Yeah. So you're doing 1,000 bands and what interactions?
They have the Coulomb interaction.
Yeah. Just one of our.
Yeah, one of our. Just the Hamiltonian that was given to you by nature, so to speak. And so we can reproduce this trend. And I won't get into where this trend comes from, that's in the paper, but you can, when you look into your calculations, you can see that they come from electronic processes that we care about great detail, that occur between the top copper oxygen layers. Because when you turn them on and off, we can immediately remove the trend. So that's all described. But the more interesting thing, I guess, is to ask what happens not in the magnetic part of the phase diagram, because no one cares about magnetism. What happens to the superconducting part of the phase diagram? So that was the next thing. And again, there are some trends, right? For example, one is this pressure effect. So you apply pressure in the plane, you raise the crystal temperature. And then there's also this layer effect. If you increase the number of layers, there's some behavior of the crystal. Okay, so again, this is never been explained, never been. And again, just skipping over many details. Oh, that's just what we showed. So this is really cool, right? So basically, you put charges into your material, right? They go into this gigantic machine, and then at some critical charge, all of a sudden there's another solution that appears, and you get a superconducting state. And because it's like a fully atomistic, for all the orbitals that you can look at it in real space, so you can actually see the pairing wave amplitude in real space, and it looks like this. There's some projection. Really actually look at really how they turn out. But the story is that, again, we can reproduce the trend. So here, this is the layer effect, here are the experimental critical temperatures. We basically, what we calculate in this calculation is we estimate the pairing gap, and then we just convert the gap to a temperature by it's roughly 4 in the D-wing superconductor. It's multiplied by 4.2. And so the computer results are these bars here. And it's not completely quantitative. So something that is about 100 Kelvin in the material, we compute to about 200 Kelvin, so by factor of 2. But you know, there are many approximations that went in, so factor of 2 is not very bad. Okay. So the end of this part of the story that we would and then finally we can actually, when we look into what is going on in the many-body phase of the problem, essentially we're solving this many-body problem of the unit cell with its environment with a diagrammatic method. So there are certain diagrams, certain Feynman diagrams going in, and you can see which Feynman diagrams contribute to a Carring solution and which do not. So we find essentially that once you turn on this class of diagrams, then all of a sudden you have very strong pairing. And if you do not, then it doesn't appear. And if you ask what is associated with the fluctuations in these ladder diagrams, they are precisely the spin fluctuations associated with the copper orbitals, which is the picture that we showed in the cartoon in the very beginning. Okay, that is the fluctuation of the magnetic background that is generating the pairing in the calculation. Okay. All right. So just to quickly summarize, this part of the talk, because I say a few minutes left with dynamics. I don't want to claim that in this exercise we built a comprehensive theory of everything going on in two plates. There's very complex materials, there are all these unusual phases, strange metals, and so on and so forth. I don't touch on any of that. But what we can say is that a direct time conditional simulation, if you give a crystal structure, now we produce quantitative trends. Something that we can infer is that although we use a full Hamiltonian for the problem, we still have to make a lot of approximations. For example, certain long wavelength fluctuations are omitted in any embedding approach because we're always simulating a finite cell. And in this many-body solver that I use, there are certain diagrams that are not included because we can't include all of them. But whatever these things that we omitted are, they are presumably just not that important for the trend. And that's, I think, perhaps important. But I think we're at a point, though, where I can begin to say I can address the question that motivates me in this field, which is how do I discover a new material? What is really interesting is that, everything in this field was discovered purely by accident. So if you look at the original motivations that Bednos and Muller had in making cuprates, the reasoning they had has absolutely nothing to do, the thing is completely wrong, okay? But they ended mixing something and measuring something fortuitously that led to this discovery. And then in the iron-based materials, those materials that were known forever and ever, I don't quite know, they didn't trace the history of that. I don't quite know why someone decided one day to measure the superconductivity, but they just did, and that's how the iron-based materials were discovered. And in the last couple of years, nictelates have appeared as a class of materials where under some pressure, not the humongous pressures you need in hydrogen superconductors, but under some pressures, they also display some type of superconductivity. And so that now when you say copper, iron, nickel, I know you're not chemists, but perhaps you know that they're all in the first row of the transition metals series. You might start to wonder, what about chromium, manganese, cobalt, titanium? Perhaps superconductivity is actually very common, and we just need to know where to look. And so I think that with the tools that we are building, we are starting to be in a position where we can start to ask this question computationally, where to look. Okay, so I just want to finish very quickly because on some non-equilibrium things. So everything that I've said is about equilibrium matter. In fact, everything I showed today is just about the ground state. And hopefully I've convinced you that there's a good motivation for the success of classical heuristics in the ground state. And we understand things very well. But what about quantum dynamics? Now, it's absolutely true that the classical simulation of quantum dynamics cannot always be efficient. Well, I guess you could. Okay, let's just assume this is true. Okay, otherwise, quantum computers have absolutely no reason. But you assume BQP is not complete, then classical simulation will be efficient. But I think the relevant question as a physical scientist is the question, can the dynamics of a local physical observable, of a natural physical system, in relevant experiments be simulated? Okay. And that's, I think the answer to this question is just unknown. Okay, so I think we're very early stage with respect to unknown question. And people on the heuristic side haven't put a lot of effort in yet. And on the formal side, people are still building the formal one. I think I will say that there was an experiment that happened. I'll just go this very. I won't really go to this. There was an experiment that happened that was performed a few years ago, for example, by the IBM group, where they argued that they tried to simulate a local observable under some physically motivated circuit. This looks a bit like the transverse field Python model. And you can, in a naive sense, argue that this looks like it should be very hard to simulate classically. But without going into the details of the story, the end result is that there's a very simple classical heuristic to obtain the same result. So we feel that there's some very simple way of just tracing the operator, the Heisenberg evolution, and discarding small terms. And the end result was that you could simulate the same experiment, on the max scale for 10 seconds. And what is even more impressive is some person took the same algorithm, put on the Commodore 64. That's great. That's just funny, but it just illustrates that there's a lot that, if you naively just say, I'm going to simulate this thing or do this quantum dynamical experiment, and I take some existing classical heuristic and it doesn't perform very well, therefore I cannot simulate it. It's not a good strategy because there's a lot of room for inventing new things. And some of the new things we've invented very quickly are, for example, I would just say quickly, some of you know about tensor network simulations. Usually people make statements that you cannot capture volume law entanglement in tensor networks. But as we showed with this work here, actually you can create a version where you can very efficiently capture volume law. It doesn't mean you capture everything about the dynamics, you can capture volume law in the simulation. And similarly here, I show just say there's some work that's coming out where we show that you can simulate, again, using some algorithms that, where the computation resource is temporal entanglement, that can simulate all the way from a quench all the way into the thermalized state, even in a two-dimensional system. What's considered very good. Okay, so just to conclude, okay, so Dirac said that the difficulty lies in that these laws are very complicated, and I think that's a bit of an outdated statement. So I think the correct statement is that often we can in fact solve problems remarkably well, and because we can learn from the data in the natural world. My colleague Robert Hong at Caltech has done a lot to popularize the power of learning from data. But in some sense, that's what science has been doing all the time, right? In experiments, what we're doing is we're learning from the world, and we're building it into simulations that we do. And then in other new fields, for example, in quantum dynamics, there's really just a lot of room for the invention of new heuristics. I think that's a very exciting opportunity. I just want to say this is my group. In the very beginning, Junhee mentioned that I'm director of this market center. So this is a new center we're starting at Caltech. That's a fully endowed center. We have $40 million endowment to support theoretical chemistry, broadly defined. If you consider what I described as theoretical chemistry, and you're interested, come and visit us, and perhaps you may be interested in doing a postdoc or becoming a graduate student. And so with that, thank you.
Yeah, thanks for the nice talk. I have two, but
It was so familiar.
I was like,
Oh, okay.
yeah, and question on
Yeah.
So on the
Yeah.
so how limited are you by sort of the sort of core potentials of these different atoms that you incorporate into the simulations? You're obviously not including all of them. So all electrons for every atom are.
Yeah, the 4 electrons don't do anything. So they just sit there in their essentially the particle like orbital. They don't excite out this. The particle I mean they don't really explore much of those.
The second question, I forget, but the ending of the IBM story, I remember like there put out an algorithm, people put an algorithm. I thought the IBM people think that there was still some discrepancy between the different.
Sure. Okay, let me go into that. Okay, so this is the spin on it. Okay, so the spin on it was basically we published some things like basically 3 weeks on the paper came out, 3 weeks and these were simulations that we did very quickly. We wouldn't have written it up except my institute said they're going to write something. So we wrote a 2-page paper. Like I was like in the conference, we just wrote a 2-page paper. Of course, in those early simulations, there were some, they all agreed they were all within the experimental error bar of the quantum experiment. And I have lots of friends at IBM, so it's not hard. But essentially, what they said is this is great because there are different classical results, and now the quantum computer can be used to distinguish, or this is very useful to tell which one is correct. But of course, if you just put a little bit more effort into the classical simulation, you can just convert it completely. And so essentially, this is the final published paper that we did, where everything is converged in these red dots to an error bar that's smaller than the size of the dot. And so now you can actually see the error in the quantum calculation. So I would say that you end up seeing the classical utility rather than testing, verifying quantum in this case rather than the quantum.
So this converged result for your method is this in agreement with, I guess, a converged result for the other classical methods?
So if you take eventually the flat iron group also converge the result further, that's basically an agreement with everybody. I don't think some of these other, like the Google thing was simply just saying that if you simulate a finite thing, a finite amount, it looks very similar. There's not really just an estimate, just an estimate.
I have a question, kind of twofold. So in your method, can you treat like problems that go beyond the one approximation? So like, at least like ECS, right? There's some story that like the ions.
Yeah, so
phononic way
I see omit phonons in the reflection, and one might say that's a bad thing, but phonons, I mean, they're always there and they always contribute, and that's something, So first of all, that's all possible. I mean, just some other amount of work that you get. There are other completely different parties in the group where we try to study the quantum dynamics of electrons. But in this materials setting, for the time being, that's not work. But it doesn't mean it shouldn't be done.
Yeah. So thanks for the talk. So at the first, you kind of show a message that like they're, despite like quantum order are intrinsically exponential, but there are like a finite amount of places, and then the
might not be a finite number, but that's just
yeah. So the
complexity, of course, there are lots of fractals,
right?
There are lots and lots. But we don't see them you don't really see them.
Yeah, so the cost is like then like you only need to search over this finite number of phases and plus a few refinements of the energies.
Yeah.
But on the other hand, we see in the Hubbard model, for example, resolving the ground state, like it's like really extremely.
Yeah, you need to go to high precision.
Right.
And so the question is what's the cost to get that precision?
Right.
And if we ask a question.
Yeah. So I wonder just basically like, because like on one side you have finite phases, but on the other side, like resolving these phases, kind of maybe still like very hard.
Yeah, of course.
So in the end, like especially for strongly correlated system, it might still be a hard problem. So I wonder if you have any comments or opinion on that.
Oh yeah. I mean, all this is hard, right? I mean, in some sense in science, we always try to do something hard. So if it wasn't hard, it'd be solved already. No, it is hard. For example, when I said the empirical evidence shows that the type that are commonly used have this poly 1/, precision cost, I mean, it could be 1/, epsilon to some high power. So if it was like 1/, epsilon to the 10, it would mean to get one additional digit, you need 10 to the 10 more computational effort. In my view, the regime of quantum advantage, though, in ground state simulation is primarily related to precision. because coherent quantum algorithms have a 1/epsilon scaling. In other words, to get one more digit, you just simulate for 10 times the length of time. Means there's some qualification I've said, but just the pure epsilon part is of that form. And actually, that is much better than essentially all classical algorithms outside of one dimension. So indeed, to get to lots of decimal places, it's very challenging, but it's not exponentially challenging. Why is it?
I guess sorry, we should probably stop here and then thanks the speaker again for the wonderful.